Hey guys, welcome back for another SVSU Math and Physics Resource Center tutoring video. My name is Brendon. I'm going to be your math tutor. And for this video, we're going to get into testing series using our arsenal of testing strategies. So I hope you guys enjoy the video. All right, let's go ahead and jump right into these two series that I have written out. So for this video, we're just gonna go right into the series and try to test them using our arsenal testing strategies. Okay, so for the first one, we have n is equal to 2 to infinity of 1 over n multiplied by the square root of ln of n. So if I'm looking at this, the first thing I typically try to do is just give it a quick glance and see what happens to our a of n as n approaches infinity, right? So that would be our n term test for divergence. And if the series is like pretty easily solved for the limit, then I just quick glance it. But if it's something if it's more complicated, then I would write it out and solve the limit on paper. But for this one, it looks like it's going to be pretty easy. So if n goes to infinity, this piece here is going to go to infinity, our n, and then our square root of ln of n is also going to go to infinity. So in the denominator, we're going to have infinity times infinity. And so 1 over infinity is going to be equal to 0, which tells us that the n-term test for divergence is inconclusive. Okay, so then the next thing I typically try to do is a direct comparison test. So if I look at this, then I might think about comparing it to a b of n of 1 over n, right? But we're going to have an issue with that because b of n we know is a harmonic series, and this is our harmonic series with our p series with a p is equal to 1. And then from the p test, we know that this series diverges, right? So if I'm taking my 1 over n, which is my b of n, but I'm multiplying the denominator by a factor of the square root of ln of n, right? So as n gets bigger and bigger, right? So when n is equal to 2, this piece is less than 1, but when n is equal to 3, we're greater than 1, right? And so we're more worried about the n behavior. So as n goes to infinity, I'm multiplying by this extra piece that's greater than 1 on the denominator, which is going to make my whole expression smaller. So that's the issue with the direct comparison test on this one, right? So if we have a diverging series that we're comparing it to, we would want our series to be larger than a diverging series. So then that would tell us that our series would also diverge. But in this case, ours is going to be smaller, right? So that tells us that our direct comparison isn't going to work for this one. Okay, so I'm going to go ahead and erase that. Okay, so now what's our next testing strategy? So those are kind of the first two that I always go for. And then after that, it's kind of a hit or miss. You can do a limit comparison test. You can do the integral test, the ratio test. So, and this one, just by looking at this function, it looks like something that we would be able to take the integral of. Okay, so then that's leaning me towards doing the integral test. Okay, so I'm going to specify my a of n is equal to 1 over n square root of ln of n, right? And so this is our function of n. So I can say that's similar to a function of x that is 1 over x square root of ln of x. Okay, and so the integral test says we need to check to see if it's positive, right? So if our function is positive, let me write these out, positive, decreasing, and continuous. Okay, so if our function is positive, let's check that first. So 1 over x times the square root of ln of x. Well, our n is ranging from 2 to infinity, right? And so that tells us that x is always positive, and the ln of x is always going to be positive when x is greater than 1, right? Because when ln of 1 ln of 1 is just equal to 0, and so our n is at 2, so we're always going to be positive, right? And then the square root of a positive number is a positive number. Okay, so we're definitely positive, and we're definitely our n behavior is definitely decreasing, right? So that was kind of the same thing as when we try to use direct comparison, where this is our denominator is getting bigger and bigger as x approaches infinity. So we're definitely decreasing. And we know that, okay, so we want to check to see that we're continuous on the interval, right? So we know that x cannot be equal to 0, but our n is ranging from 2 to infinity, so we don't have to worry about that. And then, yeah, so same thing here. We don't want ln to be equal to 1, because e to the what power is equal to 1, e to the 0 power, so then this would be 0, but we also don't have to worry about x being 1, because our n is ranging from 2 to infinity. So we are continuous on the interval. Okay, so now that we've satisfied those three criteria for the integral test, let's go ahead and run it. So the integral test says we're going to do the improper integral from k, which is 2 in this case, to infinity, of our function of x. So 1 over x square root of ln of x dx. Okay. So now let's go ahead and just solve the method of doing the improper integral. So this is going to be the limit as t approaches infinity of the integral from 2 to t of 1 over x square root ln of x dx. Okay, so what I'm going to do for this is I'm going to go ahead and let u equal to the ln of x, and then that's going to let me have, when we take the derivative of this, du is equal to 1 over x dx. And so if I solve for dx, dx is going to be equal to x du. Okay, so now what I'm going to do is I'm going to go ahead and plug everything back into my limit. So I have the limit as t approaches infinity of the integral, and I'm not going to put the bounds on it because I'll just substitute the bounds back in when we back substitute in for x. Okay, so the limit as t approaches infinity of, let's see, 1 over x, and then it's going to be the square root of u, so I'm just going to write that as u to the 1/2 power, and then dx we know is equal to x du. So it looks like my x's are going to cancel, and then I'm going to be left with the limit as t approaches infinity of the integral. And it looks like I'm going to move that u to the numerator, so it's going to be u to the negative 1/2 du. And then we can just go ahead and solve this using our power rule. Okay, so the limit as t approaches infinity of, so when I solve this, I'm going to raise the power by 1, so negative 1/2 plus 1 is going to be positive 1/2, so that's going to be my new power, and I'm going to divide by the new power, so it's going to be 2. 1/2 on the denominator means we're multiplying by 2 times u to the positive 1/2 power. Okay, and then this is going to be the limit as t approaches infinity, and so what we're going to do is we're going to back substitute in for our x variable. So this is going to be 2, and then times ln of x to the 1/2 power, and then we're going to evaluate that from 2 to t. Okay, so let's go ahead and evaluate that. So that's going to be the limit as t approaches infinity of 2 times the ln of t to the 1/2 power minus the ln of 2 to the 1/2 power. Okay, so now let's go ahead and evaluate our limit. So if t goes to infinity here, so our natural log is going to go to infinity, so then the square root of infinity is also going to go to infinity. So this piece goes to infinity. So infinity minus some constant term multiplied by another constant term is also going to go to infinity. So the integral test says if we're able to run the integral test and when we solve the improper integral and we get the improper integral to diverge, that tells us that our original series also diverges. Okay, so using the integral test on this one, we were able to solve for the series from 2 to infinity of 1 over n, the square root of times the square root of ln of n. We were able to solve that diverges using the integral test. All right, so let's go ahead and move down to our next series. Okay, so let's go ahead and get into this series. So we're going to start out this one with the same way that we started out the last one, right? So we're going to start out by kind of just giving it a looks over and determining what's going to happen as n approaches infinity. So as n approaches infinity, this piece here looks like it's going to go towards infinity, and so subtracting this constant off infinity isn't going to do much. So our denominator is going to go towards infinity, which tells us our function is going to go towards 0. So that tells us that our nth term test for divergence would be inconclusive. Okay, so then the next one I always try to do is a direct comparison test. So we're going to start out and we're going to let our b of n. It looks like we can let our b of n equal to 1 over 3 to the 2n. And then this is actually just going to be equal to 1 over 9 to the n, which is equal to 1 over 9 to the n, right? And so then this here is a geometric series with r equal to 1 over 9, which is actually going to be less than 1, which is going to be which tells us that this is a converging geometric series. Okay, so if we know that this is a converging geometric series, our a of n has to be smaller than this series, right? So if we look at our denominator, we're subtracting this 3 off of our initial piece that's in the our b of n, our comparison series. So if we're subtracting this in the denominator, that tells us our fraction is going to be bigger than our comparison series. All right, so that's that. So by direct comparison, it doesn't work, right? Because ours is bigger than a converging series, right? And so for direct comparison, you need to be smaller than a converging series, or you need to be larger than a diverging series, right? So we don't have that. But so since these are so similar, I'm thinking this 3 doesn't have much to do with the end behavior, right? So what I'm going to do is I'm going to do a limit comparison, which will let us know if that's the case or not. So if you remember, the limit comparison is we take the limit as n approaches infinity of a of n over b of n, right? And if we get this to be equal to a positive finite number, right? So positive meaning your number is greater than 0, and then finite means that it doesn't approach infinity, or it is less than infinity. Then that tells us that our b of n and our a of n have the same end behavior, meaning they either can both converge or they both diverge, right? So let's go ahead and plug this in. So the first thing I'm going to do is I'm going to specify this is my a of n piece. Okay, and so let's plug it into the limit. So we have the limit as n approaches infinity of a of n, so that's going to be 1 over 3 to the 2n minus 3 divided by 1 over 9 to the n. And so we're going to do keep, switch, flip. We're going to keep the numerator, switch the sign from division to multiplication, and multiply by the reciprocal. So that's going to be the limit as n approaches infinity of, let's see, 1 over, and I'm going to simplify this, so this is just going to be 9 to the n minus 3 multiplied by, looks like just 9 to the n. And we flip the denominator, it just becomes 9 to the n. Okay, so then let's simplify this, so it's going to be the limit as n approaches infinity of 9 to the n over 9 to the n minus 3. Okay, and so to solve this limit, we're going to multiply by 1 over 9 to the n divided by 1 over 9 to the n. And we can do this because this piece is just 1, so we multiply by 1. We're not changing our fraction. Okay, and so let's see what we get. So we have the limit as n approaches infinity of, so 9 to the n times 1 over 9 to the n, it's just going to be a 1 left in the numerator, and then we distribute our 1 over 9 to the n through our denominator. That's going to give us a 1 minus 3 divided by 9 to the n. Okay, so now we can go ahead and plug in our limit. So as n approaches infinity, this is our only piece that has an n in it, and our denominator is going to go towards infinity, so then that tells us that this piece is going to go towards 0. So then that tells us we're left with just 1, which is greater than 0, so it's positive, and 1 is a finite number because it's less than infinity. Okay, so from the limit comparison test, that tells us that our series converges, because we have a positive finite number, and our comparison series, our b of n, also converges. So then that tells us a of n's got to converge. All right, so in the next video, we're going to do a few more series for this strategies of testing section. And yeah, so I hope you guys enjoyed this video.